Ezzati from Team Iran. I want to present problem number 12, sound versus fire. At the first, a small flame can be put out of the sound. Investigate the parameters of the flame and the characteristic of the sound determine the whether of the flame will be turned off. The main parameter of this system is the sound SPL, the sound frequency, waveform of the sound, distance between the sound source and the flame height. This is my overview. And after, in the first step, we direct the sound wave to the flame using the speaker. The flame is the supply, but the methanol gas, the source, and the science, the gas flow is the stable and the laminar. The flame remains the steady. At the second, after the oscillatory, the displacement of the airflow caused by the wave emission from the speaker, according to the Bernoulli's principle, the pressure increases and the velocity decreases. And after the three flame agents for the turn of the flame, the sound flame, the interaction after the flame destabilization, and after is the turn of the flame or the extinction gauge. And after the equation they describe is the spherical sound wave propagation outward from the point source. The pressure at the amplitude that decreases with the distance r, and the wave oscillation with the angular velocity and the wave number. This equation gives the particle velocity u in a sound, and the wave based on the local pressure ambient, the density, the rho surf, and the speed of sound c surf. And the velocity oscillate time is at the space with the same phase at the pressure wave. After the maximum pressure, the occurs of the crest of the wave, while the minimum pressure in the front at the truth. And the science oxygen pressure is important in this phenomenon, and theoretically they reformulated the pressure, the equation to the account for the partial pressure of the oxygen. To do this, the pressure, the equation is multiplied by the 21%, have the effect to the volumetric, the concentration of the oxygen of air. And after, the possible threshold, the condition for the extension is the when the flame height becomes the comparable and or the exceeds the acoustic wavelength, and this is the positive the threshold because the system the transition from the stability to the instability to control the parameter. And after the maximum the threshold level, the acoustic pressure before the extension is the function of the both time and the flame height. As the longer that's the taller flame, the shift the stability threshold due to the energy transfer and the larger interaction volume. And after although the wavelength is the temperature dependent, the effect of the temperature variation on the sound. Propagation can be neglected here. The sounds, the phenomenon occurs with the short duration in the 3 seconds. This phenomenon is dependent inside the control pressure chamber. And after, let's go to the flame model. It's after we drag the critical line for this system, and when the PO critical is higher than the PO is the function of the dt, we can understand my system is the turn off. Is this equation the function of the distance, actually the flame height, and the time dependent this phenomenon. After this equation, the model of the temperature distribution in the flame under the cylindrical symmetry. The first term, the acoustic for the thermal diffusion, while the second model, the effect of the sound-induced the pressure oscillation modulated by the oxygen concentration. At the flame, the center is RCF, the R equals 0. The radial derivation of the pressure and the temperature are set to the 0 to the precede the symmetry. At the flame interference, the R equals R0, the continuity of the pressure and the temperature is imposed to avoid the physical improvement. And after, we measure the numerical we have the numerical calculation with the MATLAB code. And after, the equation describes the displacement of the flame, the surface under the influence of the unsteady flow, and the sound wave, the term related to the flow velocity and the flame propagation. And the acoustic oscillator, the indicated the sound wave can affect the flame stability by altering the flow structure and the reaction rates. Let's go to the experimental result. At the first, for the simulation with the console, we defined the geometry and selected the pressure acoustic frequency during the model to simulate the harmonic wave propagation in the air. The source, the boundary condition where the actually confirm to the LO wave, the reflection and the resonance. The simulation shows the real part of the pressure field inside the tube. The standing wave are clearly visible with the news, and Ancient of that the result from the wave interference. A key factor is the acoustic and the flame interaction. Let's go for the experimental setup. At the first we use the amplifier, the speaker, camera plus the fixed stand and the burner, actually the Hossein burner. And after for the experiment device are the function generator for the control the frequency of the system and the change the type of the wave, and after use the power supply for the turn on the amplifier in the system. But due to the transition of the turbulence the flow near the flame, the frequency is not controlled with the flame the extension. But we make the new experiment setup for this phenomenon. We use the bikes to control the oxygen, and after by using the 100 micrometer mesh to airflow becomes the laminar. And after, we use the cone in this phenomenon, and without cone, as you can observe, the pressure loss is higher than when you use the cone. After, in this experimental setup, we use the thermal camera for the observe the better this phenomenon, and as you can observe, we can measure the temperature, and after observe better this phenomenon. And for the pressure measurement of this phenomenon, we put the flame in the bikes, and we attach the gauge of the pressure, and with the actual airflow, we count the airflow from the bikes, and after we observe in the which gauge of the pressure our system is turned off. Let's go to the experiment verification. We plot the displacement versus the chart, and after the plot the FFT, as you can observe, we have the some noise, but we have the peak of the wave have the good fit together. For the image processing, as you can observe, it's the actually 0.5 to the 1.5 second. We have the same motion, but after the 2 second, my system will leader turn off, and after in the 2.5 second, we can observe the resonance of the system, and in the 3 second, my system turn off. And after for the pressure chart, we use the sensor pressure in the 3 location of this. In the first of cone, in the middle of cone, and in the end of the cone. And as you can observe, the pressure in the actually first of the cone is the higher that's the all, and at the middle and at the end, because we use the cone in this situation. Now let's go to the phase plot. The time for the 1 second, the 1 second the flame the more to extension to the higher frequencies where the acoustic pressure exceeds to the extension their show. And observe the L extension the points, and around the 200 hertz suggests the initial instability zone from the rapidly under the science the acoustic forcing. And after the 2 second, we propagate the extension the region expands to the shift in descent the dynamic the show the behavior is that the flame interact and with the range the frequency mode. After the experimental extension data the near the raising the slope at their show the curve impulse and the transit the build-up of the acoustic energy the critical level by the stabilization. And after the 3 second the extension the show and becomes to the more structured the shrink the multi the location the peaks the flame oscillation and the transition to the shape of the extension. Let's go for the parameter analysis. At the first in the sound frequency, as you can observe, before the 18 frequency we have the extension, and after we can observe that this system is the not extension. Why? Because my system goes to the anti-phase mode. And so after from the sound frequency, the sound pressure versus the frequency, as you can observe, before the 2000 Pascal, we can observe my system is extension, and after is a non extension in the D's, and we have the great fit between the theory and the experiment. And after from the sound pressure level is the maximum velocity versus the sound pressure level, as you can observe the between the 0 to the 16 we have the not extension, but in the 60 between the 100 we have the extension, and after the 100 my system goes to the anti-phase mode. And after the simulation, this plot the response of the SPL distribution the along the tube is disable the zone of the high the SPL is trying the acoustic energy that can influence the flame shape or the event the extension is. And after the waveform of the sound, we check the 3 waveform is the triangle, a square, and the sine wave. And as you can observe, the plot, the theory chart is the before this the extension and the not extension, and exactly the time versus the sun pressure we have the same motion. And after the theory versus experiment, we have the good theory, we have the good fit between the theory experiment. And why? Because error is so tiny, you can observe the error bar in this chart. And after we plot the relation, we plot the versus the max plane versus the distance. It's done after, as you can observe, my system is not turned off. But after is the higher is the top of the chart, my system is extension. And after the flame, the zero the velocity at the distance of the 0 centimeter from the sun source. And after goes to the flame height. Flame height is the before the 2 centimeter. As you can observe, we have the max velocity, but my system is not turned off. And after this, as you can observe, my system is the extension zone. And we have the good fit between the theory and experiment. Let's go to the conclusion. At the first, I check the main equation, then investigate the wavelength, then make the critical line with the partial pressure and the PD equation for the sound total versus fire. This is the problem. And next one, check the experimental setup. I make the 2 experimental setup for this phenomenon. At the first was a good result, but the pressure is not controlled, and we can have the theory versus experiment because the frequency don't have the relation between them. Turn off the flame. And after I use the one of the girl technique for the find in the which pressure my system is turned off. And after the experimental result, we have a good fit between the theory and the experiment, and I use the simulation for the numerical calculation and the both. And I use the systematic error because my systematic error is higher than the non-systematic error is the outcome part in the experiment, and because I use the same error bar in this system. This is my references, and thanks for your attention.